on essentially finding what they are going to call derivatives. I'm actually going to tell you today what a derivative is, although you kind of know it, you just didn't call it that. Right, over here are the two main formulas that we're going to use to calculate the slope of a tangent line at a given point A. This one up here you should use for polynomials. This one here tends to work much better with square roots and fractions. And that's essentially where we are right now. Now over here, the first question I want to deal with is an application, a bit like yesterday we started with applications. This one is asking us to find the average velocity in this interval, let's say from 4 to 8. So I'm just generalizing it from A to B. S is the position and T is time. So you want to know the average velocity. It's essentially the difference in position divided by the difference in time. So this would be the value of the function at B, take away the value of the function at A, divided by the time B, take away the time A. So if you wanted to find the average velocity from the 4-second mark to the 8-second mark, so if you imagine this is a moving object, how on average, what was its velocity in that interval? What you would do is apply this formula that I've just written up here, and you would get that the average is the value of the function at 8, because that is B. Take away the value of the function at 4, and then do 8, take away 4. Right, 8 take away 4 is 4. That's a bit messy, but that's what calculators are for. So here it goes. 1/2 times 8 squared. I could do it in my head. All right. 8 squared is 64. Half of 64 is 32. At least I can do part of it in my head. 32. Take away 9 times 8, so take away 72. And then add 15. I was not expecting a negative number there. But that's okay. Negative numbers are allowed. So negative 25. But then I'm going to take away the value of the function at 4. So 4 squared is 16. So that's going to be 8. Take away 36. Add 15. And that's going to be take away negative 13, which is essentially add 13. So that becomes negative 12 over 4. And the answer is negative 3, which it is. Velocities, if you're not into physics or you haven't done any physics classes, that might surprise you that you could have a negative velocity, but it's not really that unusual. If you think of position as maybe a vertical distance, a positive velocity means that at that point in time, the thing's going up, and a negative velocity means it's coming down. So positives and negatives are okay, they are. Now you could change that interval from, 7 to 8 to 7.999 to 8. If you move closer and closer, let's say to 8, you'll eventually get what's called the instantaneous velocity. That would be if you were in the object that was moving and you looked at the speedometer and you said, okay, 8 seconds, and you looked at the speedometer, what would it be going at? That's kind of your instantaneous velocity. And you get it from one of these two. Now, since this guy is a quadratic, great, should I use the top one or the bottom one to find the instantaneous velocity? Use this formula, or should I use this one?
The H one?
Yeah, why not? Actually, can't you use either? But I suggest you use the top one because it tends to be easier. That's the only reason. So there's no right or wrong answer to that in the sense that both work. But the top one is better for polynomials, cubics, quadratics. And again, this one is better if it's square roots or fraction, right, rational functions. So I want to find the instantaneous velocity. That's essentially the slope of the tangent line. So we're going to do the limit as h tends to 0. Since this is called S, I guess I could adjust the formula a little bit and do a plus h, take away the value of the function at a, all divided by 8. And so that is going to become the limit as h tends to 0 of, that's essentially a, the value of the function at 8 plus h, take away the value of the function at 8, all over h. We've done quite a few of these, hopefully by now you're getting a little bit more comfortable with them. See what we get. S of 8 plus h, well, that's going to be 1/2 8 plus h squared. Take away 9 lots of 8 plus h, add 15. Take away the value of the function at 8, and we already found the value of the function at 8. It ends up being negative 25. If you FOIL this out, you get 1/2 of 64 plus 16h plus h squared. Distribute that, you get 72 take away 9h plus a 15 plus a 25. If you find a half of these terms by distributing it, you get 32 8h and 1/2 h squared. And well, I guess I could tidy up those numbers, but I'm not going to. I'll do that the next line. And let's collect like terms. I have a 32, I have a 15, I have a 25, and I have a negative 72. And something quite remarkable and very nice happens. Don't they cancel each other out and you get 0? So if you add this to that, that's 32, 40, 72, take away 72, gone. If you then focus on the h's, there's an 8, take away 9, so that's negative 1h, and there's a plus 1/2 h squared. And if you've done this correctly, the top line will always have something with h's in it. If you've got a +4 left over or something weird like that, you're just wrong. Go back and fix it. Now at this point, you pull out a common factor of h. And I forgot, so I'm going to put it in right now. It's the limit as h tends to 0 of everything that we've just done. So we can cancel. Now we're going to be looking at the limit as h tends to 0 of this guy. And at this point, you can just replace the h with 0 and you get -1. And that number that we've just found is the instantaneous velocity. Are you comfortable with that question? Because you can follow it. Right. And that is basically what question 11 is about. And they do a little graph thing, and we can certainly look at that, but not right now. And we've got a really a one-off question straight after that, which I'm going to show you right now. And that'll work. So when you look at this graph here, oops, it's basically a distance time graph of two runners. One of them is the red guy, A, and his position with time is that straight line, and B, the curved one. Now, if you imagine there's a lot of information going on there, but if you imagine what kind of race each one of these runners is doing in a 100-meter race, they are not running the same race. They're running it in a different way, right? Let's look at A. Because that is a straight line, is it the tangent line? Basically the slope of that line. What that tells me is that runner A, when the gun goes off and he starts running, whatever the number is, let's say it's 9 meters a second, right? He starts running at 9 meters a second, right? And he keeps that pace all the way to the end. On the other hand, if you look at what's happening to runner B, right, bang, the gun goes. You see he goes quite slow. You see the distance, and then he gets faster and faster and faster. In fact, is it B a more realistic way that people who run the 100 meters run? Don't you start off relatively slow, and then you get faster and faster, right? As you know, the 10 second, in this case, 13 seconds goes by. So there is a description of the races, and one of those kind of describes what I just said. Now, this question is, how long after the race began in seconds is the distance between the runners the greatest? And how long after the race began in seconds do the runners have the same velocity? Now, those are quite subtle questions. Right. If you take vertical cuts through this graph, right, going up and down, the distance between the red and the blue, the vertical distance, isn't that how far apart they are? So can you imagine the guy that's going constant speed? At the start, wouldn't he pull away from the other guy because he's going much slower? And then how far away do they get? Well, this is a judgment call. And I'm gonna go, that's 1 3/4 of a box. And that's 1 and, yeah, I would say it's about 1 3/4 boxes. Are you with me? That, you know, the biggest gap from top to bottom is about 1 and a bit boxes. And each box is worth 20. So I'm going to go. Oh, they want to know the time. Oh, okay. Then if it happened here, all I would do is put in 8 seconds. And then it says, how long after the race began in seconds do the runners have the same velocity? Now, if you take that point there and you draw the tangent line, it's not quite as steep as A. If you take this point here and you draw the tangent line, it's steeper than A. So somewhere between 5 and 12, there's going to be a place where the tangent line and the red line are parallel. And that's a judgment call. I'm going to go for 8.5. And since those were judgment calls, I'm going to hit key. Do you think I'm going to be right in both? No, you disagree? Right, let's see how bad my guesses were. Okay, where are you hiding? I think you're up here, aren't you? No. How can you lose a question?
It's question 12.
Thank you. I am bad at guessing. Was that the numbers you were thinking rather than mine? evidently at 9.5 seconds. Let's have a look at 9.5 seconds. Right, 8, 10, 9.5. Ooh, okay. I said 8 and they said about here. Yeah. I don't think I'm that wrong, but whatever. And that is a kind of one-off question. And that's how you could do it. And now let's go back to math. We've been spending a lot of time using the two formulas over here. Let's take it one stage further. We're going to find what is called the derivative. And here it is. The slope of the tangent line to the curve y equals f of x at x equals a is called the derivative at x equals a. And we use this notation. Instead of m, we will now use that notation. And you say that out loud, f dash a, or f prime a. I don't like f prime, because we don't call it f prime back home. And I can't remember to call it f prime. So you'll hear me calling it f dash. Do you call that little funny tick mark prime? Is that what you normally call it? Do you have a name for it? Anyway, you're going to call it f dash a from now on, right? Just that way I'm using the same word you're using. Makes it easier to communicate. And that is what a derivative is. A derivative is essentially the value of the slope of the tangent line at some given point A. So you're going to get a bunch of questions, which are really the same questions that you've had before. But they're going to say, well, they're going to ask them in this way. Use, and I'm just going to call this guy 1 and 2, so I don't have to write it down, right? Use 1 or 2 to find f dash of a. And then they might say a equals -1. Then they'll tell you a function. It's a horrible looking one you start with. So we are going to find f dash of a at a equals -1. And this is going to be the function. It's actually more efficient to just say this. Doesn't that mean the same thing as that? You see, that's a much more efficient way of asking me. So this is saying, find the slope of the tangent line to the function f when a is -1. And the function f is this guy. Any preference? Do you want me to do 1 or do you want me to use 2? I'm looking for a volunteer here. You want me to use 1? Do you want me to use 2?
One.
Good, because if you'd said 2, I was going to say I'm not doing it with 2 because 1 is for polynomials. So here it goes. F dashed a is the limit as h tends to 0 of f of a plus h, take away f of a over h. Do you see the only difference is the m, the slope of the tangent line, is now being replaced by that guy. I mean, that's the only difference. There's very little to worry about except that. So when I put in f dash -1, that now becomes the limit as h tends to 0 of -1 plus h, take away f of -1 over h, right? I'm just replacing the a with -1. So f dash -1 is going to be, the limit as h tends to 0 of a really ugly, doesn't look ugly maybe, but it is, that guy. And f of -1, well, -1 to the 4 is 1, so that's 9. So you're basically taking away 9. And at this point, you're going to trust me that -1 plus h to the power of 4, doesn't that need to get FOILed out? And you can imagine that's going to take a lot of multiplications, isn't it? Because it's going to be -1 plus h times another one times a third one times a fourth one. So you're going to just kind of trust me when I say the answer is 1 minus, let me show you a little trick. I can actually do any power of 2 things added or subtracted, like these 2 guys here. I'm going to use a little guy called Pascal's triangle. Now, you don't need to worry about this if you don't like it, and that's fine. And if you do like it, you may want to use it. This is how Pascal's triangle works. You start with the 1, then you go 2 1s, then you go 1 2 1, 1 3 3 1. And finally 1 4 6 4 1. Has anybody seen a triangle pattern like that before, called Pascal's triangle? Now you can use Pascal's triangle to find out what that is equal to without having to FOIL it. Now I want to, in this case, I want -1 plus h to the 4. So I'm basically wanting that guy. And so the numbers, the coefficients are going to come from this row, right? The one that has a 4 on it. And the rules are x to the 4, which is this guy, plus 4x cubed y, plus 6x squared y squared, plus 4xy cubed, plus 1y to the 4. Do you notice that the coefficients, the 1 4 6 4 1, go here? 1 4 6 4 1. You start off with the first guy, 4 powers. Then that guy reduces by 1 and you get a y to replace it. Then it gets reduced another 1 and you get another y to replace it. Then it gets reduced by 1 more and you get another y to replace it, and then you get this one. Now in my question, which was -1 plus h to the 4, the x is -1 and the y is h. So I will get -1 to the 4, 4 -1 cubes h, 6 -1 squared h squareds, 4 -1 h's, and then h to the 4. And so a 1, -4h, plus 6h squared, take away 4h cubed, and add an h to the 4. So 1, take away 4h, add 6x squared, take away 4x cubed, plus h to the 4. Do you like Pascal's triangle, or there's just too much work? It's your choice. I'm just giving you an option if you have to FOIL something that's really big and ugly. And for instance, that one there is what you use when you want to do, you know, a plus b cubed. That's a plus b squared. So back to our guy. it's the limit as h tends to 0. Distribute the 9. 9, 36h, 54h squared, 36h cubed, and 9h to the 4. And the only decent thing that happened here is that the numbers cancel out. So I have this guy, this one, third term, fourth term. Almost done. What do I do to this top expression? What's the next step? What do we do to this?
Factor.
And you factor out. What is it you factor out? You're right.
3h.
Oh, you could do more than that. I hear you. And 3h would actually be the sensible thing to do, but don't do it. And you say, well, why should I not do it? It's just less work if you take out the h. You see? Not that you couldn't take out 3h, I just wouldn't. It's just not worth the work. In fact, when you do these questions, won't you always factor out an h? That's just the way they work, right? There's always going to be a common factor of h on the top. And so we are looking at the limit as h tends to 0 of this guy here. And I have no idea why I put a line there, because you don't need one. And now you can make h 0 and bingo. The answer ends up being negative 36. Are we okay with that question? It was quite a, it was quite a long question. A lot of lines of working. I would suspect that when you're doing the homework, won't you be able to combine 2 lines into 1 line, skip a line here, do some in your head. So you could maybe reduce it by, I don't know, 3 lines or so. But this is like every line that you could possibly need example. Now, in that particular question, we're only finding the derivative at -1, right? We're only finding the slope of the tangent line when x is -1. So I use both phrases. Well, the next phase of the process, an example is 15, where you're given a function. And you're being asked to find f dash of a. So they're not giving you a number. They're not saying, find, find f dash of a and then tell you a is 2 or a is 10. They're just leaving it as a general a. So the limit as h tends to 0 of f of a plus h, take away f of a all over h. Do you know those little wooden things that you stick in ink and you go stamp, stamp, stamp? Wouldn't it be really good to have one of these so that you could have that guy and just go stamp? Or even this little guy and go stamp, 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 because it's really boring writing that, doesn't it? So what have we got? 2 lots of a plus h squared, take away 4 lots of a plus h, add 3. Take away f of a. So it's going to be 2a squared, take away 4a, add 3, all over h. Okay, if you do a plus h and you kind of do, well, either Pascal's triangle or just FOIL it out, you'll get that guy. Then you get minus 4a minus 4h plus 3. And if you take all this away, you get take away 2a squared, take away takeaways, add 4a, and then take away 3. Distribute the 2, you get 2a squared, 4ah, it's an h squared there, 2h squared, minus all the other stuff. Okay, now we get to have some fun. There's a lot of stuff going on this top row here. Can you see anything that gets cancelled out by something else?
The 3's cancel each other out.
Okay, dead.
All the
Anything?
numbers, like the 49, 4a.
4a, yeah, it looks like a 9, doesn't it? The 4a gets cancelled out. Anything else?
2a squared.
And the only pieces that are left alive are a 4ah, 2h squared, and a minus a 4h. Would you agree that's a lot nicer than it was a few moments ago? And so here's the little thing that you should be looking for. When you get to this part of the working, the terms on the top, all of them should have at least one h attached to them. To say there's an h, there's an h squared, there's an h. If you have a plus 2a or a minus 7, right? A little orphan thing left over, stop, because you're wrong, right? If you've done this correctly, when you reach this line of working, all the terms on the top will have at least have an h in it. Secondly, once you reach this line, the last 2 lines are pretty much guaranteed. You will pull out a single h as a common factor. Every single time, right? Pull out an h as a common factor. Every single time, you'll then cancel that h. And you'll be left with whatever you happen to be left with, in this case, that guy. And then at this point, every single time, you'll replace the h with 0, and the answer that comes out is that. So we have found that the slope of the tangent line at A is 4a take away 4, right? We have found f dashed A is this guy. I can now use that, and working with this function, that's where it came from, I can tell you this. Do you know the slope of the tangent line when the x coordinate is 2? Is 4. The slope of the tangent line when the x coordinate is 0 is negative 4. You want the slope of the tangent line 100? Once you've got this guy, can't you find the slope of the tangent line to this quadratic at any place you like without having to do any extra work? Don't you just use this formula? 4 times whatever a is, right? The x coordinate is a. 4 times whatever the x coordinate is, take away 4. Is that helpful? I think so. That's kind of cool. Now, we know what quadratics look like, right? I'm not saying this is the accurate version, but won't this one look like a happy face? Because quadratics look like happy faces. If I choose the vertex, right, that guy there, wouldn't the tangent line be a horizontal line? Would that make sense? What's the slope of a horizontal line? What number is the slope? 0. Now, if f dashed of a just tells me the slope, then doesn't that mean that 4a take away 4 will be 0? Agreed? And if you solve, don't I now know the x coordinate of the vertex? Do you see how I managed to find the x coordinate of the vertex, right? By simply using this fella and finding out when he's 0. Because when you think of all polynomials, right? You know, a cubic might look like that, for instance. Won't there be 2 vertices, right? I can find the x coordinates of these by finding what f dashed of a is and then solving for when it's 0. So we now have a very efficient way of finding local max and mins. Find the derivative using a's and solve for 0. I think that's pretty powerful. Any questions? Are we good? Right. You have hung in there through thick and thin and a lot of really cumbersome equations. And we are eventually reaching a place where we can find the shortcut to these guys. Would you agree, aren't these questions, 10, 12 lines of working just to find out what f dashed 1 is or f dashed 2 is? Wouldn't it be really nice if there was a shortcut method? You ready for it? Right, here goes.
You're lucky we're all sitting down for this.
I'm going to put on this side what the function is, and I'm going to put the derivative, and I'm not going to call it f dashed a anymore. Let's just call it what it is. Isn't a the x coordinate? So you might as well just call it f dashed of x, right? Now, I'm just going to write down some examples of a function, and then next to them, what the derivative of that function is. And we'll see if you can find some patterns. If you start with the function 3x squared plus 10x, its derivative, used to be called f dashed of a, is now going to be called f dashed of x, is 6x plus 10. If this guy is x cubed, you get 3x squared. If this guy is 4x minus 1, you get 4. If this guy is 2x squared minus an x to the 4, you get 4x, take away 4x cubed. Now just look at those 4 examples for a minute and try and figure out how you can use these guys, the original function, to find out what the derivative is. Can you see any connections going on here?
Yes.
So look for patterns. And the pattern is to kind of be the same pattern for everything, right? Does anyone want to try their pattern out on that one? Because if you give me the right answer, it means you've figured out what the pattern is.
Sure, I'll try it.
Go for it.
So the first term would be 20x to the third, then minus 4x plus 6.
You nailed it. Can you see that? Okay, I know at least one person has figured out the pattern. So you're not allowed to answer the next one. You're just going to sit back in your laurels and enjoy the pain of the others. Somebody different, tell me what the derivative of that function would be.
I want to do it.
Go for it.
20x to the 9th and then minus 3x to the 2nd.
You've got it. Harmon's got it. So he's off the list. Just one last one, and then I'll tell you the rules. Or rule it again. Anybody, with the exception of 2 people, want to have a shot at that one? I know you want to do it, Izzy. Come on. You want to have a shot at it? We'll all laugh at you if you get it wrong, because that's what kind of class we are, right?
I mean, okay, let me bust out my calculator for this.
Sure.
Okay, 64x cubed.
Correct.
Oh, espérate. Minus 36x 8, because I don't know what that would be called.
That's as good a name as any.
Plus 1?
Yes. Correct. So we call this rule the power rule. Can you imagine if you had to use rule number 1, how long it would take you to take the derivative of this guy? Can you just imagine a plus h to the power of 9? Can you imagine? You don't want to imagine it, right? Nobody's going to do it that way. So what we've got here is basically a rule, a formula, a pattern, whatever way you want to phrase it, that allows us to take polynomials and find their derivatives. And this is the generic version of that formula. Ax to the n, that's like 7x cubed, right? You just need to focus on one piece, because each piece, the same rule works, right? So the rule that made that answer this is the same rule that made this guy that, right? So you only need to say, what does 1 power of x get you? And the rule is written down like that. In English, to me, it makes more sense in English, is multiply by the power and then subtract 1 from the power. And you will hear me say this so many times you'll get fed up hearing it, but it's a good way of getting into your head. That is a formula, but formulas don't stick in people's heads as much as, I feel anyway, sentences can. So the rule is multiply by the power and then subtract 1 from the power. Got that? The rule is multiply by the power and then subtract 1 from the power. So let's show you that working. Suppose I have a function, 4x to the 7, take away 2x cubed, right? And I want to find its derivative. You multiply by the power, and then you reduce the power by 1, right? Multiply by the power to get 28, and then reduce the power by 1, right? Multiply by the power, and then reduce the power by 1. I mean, as far as rules go, would you agree the power rule's not the weirdest one in the world? I mean, it's relatively easy to remember, right? Multiply by the power, reduce the power by 1. And this rule is still true, even although what I'm about to do next might look like you're not doing the rule anymore. I am. I'll show you what I'm getting at. Find the derivative. Shouldn't have problems with this one. Multiply by the power and reduce the power by 1. Technically, that. But we never write that, don't we? Just write 6x. That's not a biggie. Now this one, I'm going to actually put the 1 in. You multiply by the power, and then you reduce the power by 1. Technically, 0. But isn't x to the 0 1? And so you get 2. So isn't the derivative of 2x just 2? Does that make sense? So, where was we did one of those guys? There. You see this one here? Do you see that 6 makes perfect sense? I don't really use the rule when I do 6x. I'm kind of lazy. 6x gets you 6. 22x gets you 22. Minus 1,000,000x gets you minus 1,000,000. Don't you just remember to stick the number down, forget about the x? I mean, it is technically the rule. Now, what about this fella? Multiply by the power, reduce the power by 1. Done. 10x's just get you 10. That's the easy way to remember them. What on earth does a number on its own get you?
0.
0. What made you think that? Because you're bang on right. Does it just make sense that it shouldn't be there? Good a way to remember it is as any. Any constant term, right? Minus 20 plus 40. Anytime that happens, the derivative of it is 0. If you want to see the formal reason why it's 0, technically speaking, couldn't I very artificially call 3x to the 0? Right? Because there's an x to the 0, 1, so 3x is 0. Now, if you use the power rule, don't you multiply by the power? Oh, 0 times something gone, right? So that's the reasoning behind why it goes. But in practice, when I see 10x, I just know it's a 10. And when I see a number, it disappears to 0. So they are the power rule, but I can have a little baby sub rule. 10x's get you 10 and numbers get you nothing, right? That's kind of tagged on at the end because it's easier to do it that way. Is that not cool? That we now have a very shortcut way of getting the answer. And some of you should be thinking, then why in bloody heck did we spend the last 3 days doing 12-line algebra questions when I could have just told you the shortcut and did it in 30 seconds or less? Well, it's to do with the fact that if I had to, couldn't I prove all of these answers were that using method 1 or 2? So the gist of it is, yes, I know how to do it from scratch to get the answer. And once I know that I can do it and I'm comfortable I could do it from scratch, isn't it okay to use a shortcut? Analogy. I know how to multiply a 4-digit number by a 5-digit number by hand. Right? I can do it in a piece of paper. I know how to do that. But won't I use a calculator when I have to do it? Now that's okay because I know how to do it by hand. If I don't know how to do it by hand and all I know is the calculator, I really don't know what I'm doing. Aren't I just hitting buttons in a calculator and it pops out with some answer and I'll say, okay, that's what it says. I don't know why it says it. You know, if I just showed you the rule, wouldn't this be, it's some kind of magic rule that you do this and nobody knows, you know, where it came from? No. If I went and said, look, you don't believe me? Use one of our rules. Is it still here? Yeah, use that rule. Go and get the answer. Okay, I believe you now, right? And it gives you a better understanding for it. But we have done that to you a lot in your life in math. We don't tell you things that could make your life easier, i.e. shortcuts, because we want you to be able to do it by hand first, because that's how you get a grip of the math or the structure behind things. And I'm now going to finish with a really cool thing, I think. Can you remember the quadratic formula, right? AX squared plus BX plus C. Wouldn't that represent every quadratic in the universe, right? A different A, B, and C, you've got it. Does anybody remember the formula for the X coordinate of a quadratic? I know it's ages ago, but does anybody remember it?
Carter, I want to give you something.
There we go. It's negative B over 2A. Right, so that guy there has an X coordinate of negative B over 2A. Does that ring some bells for some of you? Quadratics, X coordinate. Watch what I'm about to do. The derivative of AX squared plus BX plus C. I want you to think of A, B, and C as just numbers. So you multiply by the power and you reduce the power by 1. What will the derivative of BX get you? Like 5x would get you this and 10x would get you that. What would BX get you? B, yes. And what would a plus number like plus 7 or plus 10 or plus C get you? Nothing, right? So this quadratic, its derivative is this. Now, at a vertex, the derivative has a slope of 0. And I am now about to solve for x. Any function that you could write down, you can find its derivative eventually. And once you know its derivative, can't you tell where these guys are? Because all you do is you make the derivative, whatever it is, equals 0 and solve for x. And it's a good place for us to finish. So last name,